Wait for maybe a minute for Mateusz to rejoin again. I can write down the title. Koshin, would you mind like checking with Mateusz maybe on like Discord or something to see if?
Yeah, I'm just messaging him.
Okay.
Messaging him on Discord now.
Okay, oh, maybe just get started in the meantime. So the I guess in the past 4 weeks we've mostly been talking about or kind of operating in this framework of reinforcement learning. And then for these last 2 weeks, that we can shift gears a little bit and talk about what's often called statistical learning. And as I say, it's like it's very similar to reinforcement learning, but it's sort of a slightly different framework. And I would say it could be maybe called a special case of reinforcement learning, but it has its own like terminology and everything. So we'll start by kind of going over the setting here. So I guess the main difference is that in reinforcement learning, we had the setting with the environment and the agent, and then they were kind of interacting with each other. In statistical learning, I guess one way to say it is the environment is fairly passive, so it like doesn't really care about what you do. So it's more about just like, okay, here's a certain environment which will be captured by a distribution or a function, and then the agent is basically just trying to observe and make predictions about it instead of having these interactions through the actions. So that would be the kind of main difference. And then the setting is going to be we'll have a set called X, which is often called a domain, and the set Y, which we call the labels. So I guess maybe the kind of example to have in mind is like image classification. That we have the domain, which is a set of all images, and then the labels are like cat and dog or something. So this is the kind of setting we're thinking of now. And in fact, a lot of the time we're just kind of, for simplicity, assume that we just work in a binary label. So it's kind of a classification problem with two labels. Just for simplicity. Of course, you could take Y to be real numbers and talk about regression and that sort of stuff. It would still make sense mostly in this framework, but I think it's a little simpler to just keep classification in mind. And then we're going to have a distribution, or talk about distributions over the set X plus Y. This is a distribution. This is kind of the underlying distribution from which the data that we observe comes from. And then the data that we observe is some tuple of data points, or let's say an M-tuple of data points of points in the domain and the corresponding labels. This is called the training data. And we'll typically assume that it's sampled IID from D, which we're going to write as sampled from D to DM. And then, so based on this, based on
what do you mean we should think about it as sampled from that? Like that D is oh, okay. Yeah, no, I understand now.
It's sampled independently and identically distributed from D. So each pair of X and Y is sampled from D, and then you sample it independently M times. And then we can talk about a learning algorithm. Which I guess we move away from calling it pi because it's not really a policy anymore. I just call it alpha for algorithm. So it's something that takes in a certain training data of a certain size and outputs a predictor, which is a function that assigns labels to the domain, to elements of the domain. So I guess the output of alpha on a training set S would be like a H equals alpha S. It's a function from X to Y, so something that tries to predict the kind of functional relationship between X and Y. And yeah, and then I guess similar to before, we can restrict to a hypothesis class. H, and this time it's a subset of functions from X to Y. Yeah, Matesh has a question of, are we assuming that the distribution comes from a certain function, if I said the question correctly?
Yeah, basically.
Yeah, so I'll come back to that in a few minutes. We're basically, we'll make it explicit when we do assume that, and there will be a what's called realizability assumption, which we'll talk about in a little bit more. And then we also consider a loss function, which you can define different loss functions for different setups, but if we restrict to classification, I guess one natural sort of loss function is what's called the error or the risk, which is just given by the probability under this distribution D that if we sample sample XY from the probability of HX not being equal to Y. So this is called the error or risk. So yeah, you could use other loss functions too, but for simplicity, we'll just mostly be considering this one. Right. Any questions about this setup so far? Okay, and then so this is our setup, and we can talk about learnability, which again will have a similar flavor to reinforcement learning, but it has its own name. It's often called pack learning, where pack stands for probably approximately correct. And then we'll see in a second what this probably and approximately refer to. So let's say, can write down a definition of pack learning. We say that the hypothesis class H is pack learnable if there exists a learning algorithm alpha which learns it. So let's just say I guess here we're assuming the learning algorithm outputs hypotheses in the hypothesis class. And there exists a function mh, which is a function from 0, 1 squared to the natural numbers, which is often called a sample complexity, such that basically for all epsilon and delta in 0, 1, so these are the kind of two parameters of how tight we require the learning to be, and delta will correspond to the probably part and epsilon to the approximately part. And for all distributions D, that was sample from, and for all m that's bigger or equal to mh of epsilon delta, we have, and then here's a condition that we have required that the probability when we sample a training data set from n samples, the probability that the loss under D of the hypothesis returned by a learning algorithm, we require that this loss is less or equal to the minimal loss across all of the hypotheses plus epsilon. So this is saying that the loss we get from the learning algorithm is not much bigger than the minimal possible loss according to our hypothesis class. And then we require that this probability be at least 1 minus delta. Okay, so this is saying, I guess assuming delta is small, this is saying that with a high probability, we're approximately correct, meaning approximately as good as hypothesis class allows.
Yeah, so I guess something that's that H here doesn't actually need to have any correspondence to D.
The hypothesis class.
Yes, like H could be like the set of linear functions, and D could be completely nonlinear. And we're just
Right,
asking,
right.
can we learn a linear approximation to D?
Yeah, exactly. Like, can we learn the best linear approximation to that to whatever distribution?
Yep, cool.
Does M here depend on the distribution D?
So the only well, this is saying that for all m that's bigger than the this mh, so basically it should be true for whenever m is at least whatever is specified by this function mh, which mh is not dependent on d. So. There's a question in the chat, which is it appropriate to think about this in terms of convergence with two parameters, one for probability and the other for approximately? Yeah, I think that's what it is. So basically, the sample complexity this is a function of two variables, and it tells you, okay, if you want this sort of accuracy, this close approximately, which is the epsilon part, with this probability, which is the delta part, then this is how many samples you need for this algorithm. So it tells you how big your training data needs to be for the algorithm to return something that's probably approximately correct with the given parameters of specifying how probably and how approximately. All right. It's like a very satisfying formalism. Yeah, it's a nice, it's a pretty concise definition, and we'll see. Yeah, yeah, it's a pretty rich kind of paradigm as well. As we'll see. Okay, so that's our main definition, and then we'll talk a bit about a few more definitions. So if you have a specific training data, x equals y to the n, we can talk about the training loss or empirical loss, which is so let's say this training data is given as points xi, yi, I guess for I running between 0 and n-1, say. And then the training loss under this training set of a hypothesis H is basically the number of times H returns the correct label or the incorrect label divided by the total number of training samples. So this is going to be the size of the set of I such that H of xi is not equal to yi divided by m. So yeah, this is the kind of empirical laws that based on that training data set. Does this make sense?
Mhm.
And then yeah, so I guess we can use this sort of a somewhat canonical learning algorithm, which is called the empirical risk minimization. Or ERM corresponding to H. So this is a learning algorithm, so it takes a training data and to return a hypothesis in H. And the way it works is that for each training data, it just outputs something in the argument of the training loss across all hypotheses. I guess with argument is not quite, doesn't necessarily return a unique thing. So I should say some algorithm is an empirical risk minimizer if ERM H of S is in the argument. But hopefully this makes sense. Or if we have some way to pick out an element of H based on an order or something, then you can also do that. Okay, so that's ERM. Any questions about these? So yeah, now maybe we can touch on what Mateusz was asking earlier, which is a question of realizability. So and the way I introduced it, I introduced a kind of general definition first and the more specific one now. Sometimes you could define and then the other way around too is, but basically we say that the realizability assumption holds with regard to H and D if there exists a hypothesis H star in H such that the loss of H star is 0. So this is saying we're in the realizable setting if there is a perfect predictor, like there's a correct predictor in our hypothesis class which predicts the distribution perfectly. Right, so and in particular, I guess I think this is part of Mateusz's question. Realizability basically implies that we can just look at the marginal distribution dx on x, and then the full distribution, the joint distribution, just needs to be given by the function h star, which we can write as So the picture here is something like, let's say this is X and Y, and then we might have some distribution of points, and then realizability means that we just have a distribution in the domain, and then this should just be like whatever is given by H star. As opposed to what Lavkush was asking earlier, like in the general setting, we don't necessarily have this assumption. So in the general setting, we might maybe write as opposed to something like having a distribution like this, where there's some noise in the y coordinate as well. So here the joint distribution is not determined by just marginal. Does this distinction make sense? So basically, in realizability, we're assuming there's a true function that generates the labels without any noise, and we're assuming that that true function is part of our hypothesis class. That's kind of a two assumptions in one.
We might also have maybe a true function, but it's not in H.
Right, that would be kind of a middle ground. Yeah, I think I don't know if that setting. I don't know if it has a name of its own, but it could make sense to consider that sometimes. I mean, I think in general, is there a question?
Can we also extend park layering to settings where the distribution is generated from some function, but with some stochastic noise? Is there a natural way to extend park layering to that setting?
I mean, that would fall under the general setting that we wrote like that. So that would be covered, because in that case we do have a joint distribution D, which would just come from the function plus some noise. So that's included there. So in realizability, it's like something more strict where I guess there's where we remove the noise.
Just to check, is this essentially a formalism of supervised learning?
Yes, yeah, right. Or actually, yeah, I think that's one way to think about it. I think in principle, it could include some sort of unsupervised learning if you don't think about the y as the kind of supervised labels with some other kind of thing, and then the last function would also need to be redefined. So you could probably include things that are a bit more general than supervised learning, but I think it's fine. It's fine to think about it as supervised learning. It's pretty much a framework that's set up for with that in mind. So that's a realizability assumption, and then so the definition that I wrote down for pack learning, the way it's written is sometimes called the agnostic pack learning. It's called agnostic. That's just to emphasize when you're done assuming or you're not assuming realizability, and then if that's the added assumption of realizability, then in the realizable setting, we can restrict to we restrict to distributions which have the realizability property with respect to h, and also in the realizable setting, this minimum will always be 0. So in that case, maybe the correct makes a bit more sense, because in that case we're really saying it's approximately correct, meaning that it's the loss is less or equal to epsilon, as opposed to the agnostic setting where we're just assuming that it's as good as is allowed by the hypothesis class. Does that make sense?
I got cut off for a moment. So the thing with that we are not assuming in the agnostic setting is only that there is an H, there's a hypothesis in the class that minimizes loss. That's the only thing we're not assuming. Or is there something else?
The thing we're not assuming is that there's not an assumption of a hypothesis which has 0 loss. Like there's always one that would minimize the loss, or at least.
Okay, that's the only difference.
Yeah, but that's actually turned out to be a
Okay.
pretty big difference. Like, I guess one way to say it is that. Yet, I guess more generally, this should be an infimum, really.
Like
Yes, it is a big difference, because basically realizability assumption, it means that we're assuming that one of our hypotheses is correct, is the entirely correct description of the environment or of whatever we're sampling from. So that is a big assumption, and often it's not a realistic assumption. Like, yeah, you cannot typically expect one of your hypotheses to be perfectly correct, but it is often helpful to consider things in the realizable setting, at least at first, because it's often just a little simpler, and then see how to generalize to the non-realizable or agnostic setting. All right. Any other questions? Okay, then maybe we can work out a specific instance of pack learnability. So here's a theorem. It's basically saying that any finite hypothesis class is always pack learnable. And we're gonna start in a realizable setting, because as I mentioned, it's usually easier, and then we'll see how it looks in the agnostic setting. Maybe I should say under the and we can write down an explicit sample complexity, which is of the form mh of epsilon delta. We can take it to be something lesser or equal than like log log of the size of the hypothesis class over delta divided by epsilon. I guess maybe. So basically, for a finite hypothesis class, we can always learn it with the sample complexity that is logarithmic in the size of the hypothesis class, and then also logarithmic in like 1 over the probability parameter delta, and also inversely proportional to the accuracy parameter epsilon.
Can I give an intuition for why?
Yeah, so I mean, I was planning to write down a proof, and maybe that will give an intuition as well. Is that acceptable? Let me know if the proof didn't give an intuition, and then I'll try to give more of an intuition. So here is a proof sketch proof. So basically, we want to show that with a high probability we end up with an assumption. I guess so. We're going to prove that ERM H learns H. So we're going to show that with a good probability, ERM will return a hypothesis which has a fairly low error. So let's write HB, which is going to be the kind of bad hypotheses. So these are the H and H for which the kind of packed learning condition inside of the probability in the definition doesn't hold. So these are hypotheses with a high loss, loss bigger than epsilon under this, I guess, let's fix a D and then epsilon and the delta. So we're taking the HP is the bad hypothesis for that D and epsilon. So these are the hypotheses with high loss. So for any bad hypothesis, we have that the probability under D of the hypothesis being correct. So if we sample xy from D, the probability that hx is equal to y, that's just by definition 1 minus the loss the hypothesis. So this probability should be relatively low then. So that's equal to 1 minus epsilon. Right, but then so by realizability, we actually have that for a training set sampled from the distribution, we have the training loss of ERM under this S should be equal to 0 with probability 1. Right. So why is this? Because ERM picks out the hypothesis from the class with the minimal training loss, but because of realizability, we assume that the true hypothesis is in our hypothesis class, which should have loss 0. So in particular, whatever ERM picks out should also have loss 0 on the entire training set.
Why is it? Why do you get probability 1 that you pick up this best hypothesis? Because what if you just don't observe one of the x's in the first m samples?
I mean, that should be fine. It's still probability 1 that you get like whatever x's you observe on all of those, there is a hypothesis which has 0 loss, so ERM will pick out a 0 loss. So,
but you might have non-zero loss on the x's outside that you haven't observed yet.
Yeah, right. Yes. So this is specifically the training loss. It's not the actual loss. So it's
Sorry.
according to
Yeah, right.
Yeah,
Okay.
sorry.
Yep. Thanks.
Yeah, this is the training loss. Yeah, that's good to point out that the actual loss could be positive, of course. So this basically says that if ERM H of S is in HB, if it returns a bad hypothesis, or just the probability of this happening when we sample from DM. This is actually less or equal than 1 minus epsilon to DM, because we just said that for each bad hypothesis to return a correct prediction, it has probability 1 minus epsilon, and that has to have happened for each of the m samples that we took in order for the bad hypothesis to end up having 0 training loss. So, and those were independent, so we get this 1 minus epsilon to the m. Does this make sense?
Can you repeat that?
Yeah, so basically this is saying ERM returned a bad hypothesis, but we just said that ERM always returns something that is correct on every training sample so far. And then we just said that for a bad hypothesis to be correct on any training sample, it has probability at most 1 minus epsilon. And then if for that to happen for each of the m training samples that we sampled so far, there will be 1 minus epsilon to the m as an upper bound.
Okay, yeah.
All right, so now we can write down a bound where we can say, okay, what is the probability under sampling the training data that the loss of ERM H of S is bigger than epsilon. So this, by definition, it just means like this happens if and only if. Sorry, I was little sloppy here. What I meant to say here is that the probability that this is equal to a specific bad hypothesis is less or equal to 1 minus epsilon to the m. And then this loss being big is equivalent to ERM just being one of the bad hypotheses. So in particular, we can upper bound this by the number of bad hypotheses times this bound that we got for a specific bad hypothesis. Sorry, maybe that's why it was confusing. This inequality up here was supposed to be for a fixed one. Does this maybe clarify your confusion, Adi?
Yeah, I think that makes more sense.
Yeah, sorry, I said the wrong thing earlier. So there are this number of bad hypotheses, and then for each bad hypothesis, this is the bound we got on the probability. And then we can actually make a loose upper bound here. We can just say that this is less or equal than the size of the entire hypothesis class. And then we can bound this 1 minus epsilon to the m. It's less or equal than e to the minus epsilon times m. And then with this bound, we can work backwards and get that this sample complexity that I wrote down once. Does this make sense? Any questions? Yeah, so here we definitely make heavy use of realizability because this part of the argument, it basically said that for a bad hypothesis, it's unlikely to always reach, or for a high number of samples, it's unlikely to return the correct label each time. But the fact that ERM gets to correct labels, or the something with zero loss that relied on the realizability assumption. So maybe I can say what a corresponding statement looks like in the agnostic or non-realizable setting. Here's a kind of an analogous theorem. It's still true that finite hypothesis classes are backlearnable. So any finite H is, I write agnostically backlearnable with sample complexity MH epsilon delta is equal to, and the thing we have here is a little bit different. I guess the thing we can prove is we have an extra factor of 2 here, and then we have this log, and also an extra factor of 2 here, 2h over delta. But this much is not that different. We just had some constant factors. But the more interesting thing is that we get an epsilon squared in the denominator. Previously was just an epsilon. So that is, I would say, the kind of real cost of going from realizable to agnostic is to have a higher power of the approximation parameter epsilon. in the showing up in the sample complexity. Um, so yeah, I don't know if we'll have enough time to prove this fully, but we can maybe just kind of sketch an outline. So we actually make use of a few definitions. One definition is what's it called? Is to say that when training data is representative. So we say training data S is epsilon representative with regard to H if the training loss on any hypothesis is close to the true loss. So there, and this is less or equal to epsilon for all H and H. And it says, Lofkush pointed out, these are genuinely different things, the training loss and the true loss according to the distribution D. So this is a meaningful definition to say a certain sample is representative if it captures the loss approximately. So for any of our hypotheses, it gives a loss that's within epsilon from the true loss. Again, and another definition, we say that H has the uniform convergence property. Respect to H. And this is like
we have H has property with respect to H.
Oh, sorry. Just has the uniform convergence property. If there exists a function which we call MH of uniform convergence, that's a similar kind of complexity function that we had earlier. It goes from 0, 1 squared to natural numbers such that for all distributions D, and for all epsilon delta 0, 1 open interval and m bigger or equal to mh uc of epsilon delta, we have that the probability for a training data sampled from D to DM of S being epsilon representative for H is bigger or equal than 1 minus delta. So this is a definition that's similar in spirit to back learning itself, except here we're just saying that the training data we end up with has a high probability of being epsilon representative. again, I guess we're at time.
Can you give
but
an example for such a hypothesis class?
yes,
Any finite?
any
one, maybe?
finite.
Okay, but one with more intuition.
Mhm. So for any, yeah, I guess that's the thing we didn't have time for. But for any finite one, we can take this to be with log. I guess log true delta or square root three. Or maybe there's a 2 somewhere probably. 2. So yeah, any finite one has this, and this is where this epsilon squared will come from. And then yeah, I think maybe next week we'll see. So for today we're just focusing on the finite hypothesis classes, but next week we'll see what happens for infinite classes, and the whole story gets a bit more interesting.
So the empirical scaling laws that have been observed in deep neural nets, could that be rephrased in terms of these notions? Because it's something about like, how many data points do you need to get a certain loss?
Right. Well, it's probably a little different somehow, because I have the sense that for those scaling laws, you also like if you have too much data, it's not good, right? So there's something a bit more going on. Because here we're just saying that we need at least that much data. So I would think it's like probably somewhat related, but probably not exactly, because I think it's kind of a more subtle thing in practice where too much data affects the training in some way too. That's doesn't necessarily improve the model that you end up in.
Okay. Yep. And then the other question is, can you phrase the curse of dimensionality just by saying that the size of H scales exponentially with X or something like that?
Let's see, curse of dimensionality. I think it's a little bit different because here we're not talking about dimension yet. We're just talking about size. Although, because in the curse of dimensionality,
Isn't dimensionality in this context basically like how like every dimension is every like point of the function from which we have this from which distribution is, like every single x mapped to some y, and what the y is for this x is that one dimension in this case.
yeah, I mean if you take dimension loosely, then yeah, that makes sense for any y. If you take, I guess y.
I guess that's the question.
Yeah, I guess
so like
my sense is
if X was like R to the D or something, then D would be the dimension.
I guess that was like
my sense of what's usually meant by curse of dimensionality is that, let's say you have a space X or space. Let's call it space A. I don't know what's a good word for space S. So if it's one-dimensional, you can take like 1,000 samples on it, and you get a pretty good cover of it, right? But then if it's two-dimensional, maybe you take like 1,000,000 samples, and then you get a pretty good cover of it. but then if it's like a 1,000-dimensional, then suddenly you would need like if you wanted like a granularity of 10, you would need like 10 to 1,000 points to get like a pretty good cover of samples from that space. So just so that's the thing that grows exponentially. So that's what I generally think of when I hear cursive dimensionality. And I guess that would apply, you know, if we took the label set to be like the interval, for example, and we wanted to represent space of functions y to x, that would be like x dimensional. So if x is a large finite set, that would have this cursive dimensionality. Yeah, so I think we can bring that in. I'm not sure what exactly the question was with regard to the relationship.
Yeah, I was just maybe hoping this could be a way to formalize what that phrase means. But maybe it doesn't
Yeah,
work.
I mean, as I understand, it just means something like this, that if you want a representative sample of points in a high dimensional space, you just need a lot of points. It's just
Yep.
to achieve a certain density of samples, which is going to be very large for large dimensional spaces.
So for cursive dimensionality, maybe we mostly mean a computational problem, while sampling is a lack of information problem, maybe?
Yeah, I agree. It's definitely a computational problem. I guess I was using the word sampling because I think that's the context in which I ran into this most recently. Like, let's say you're trying to get a sense of how a function behaves and like a high dimensional function behaves by just looking at some samples of the function. Then in like for a two-dimensional function, you can get like 1,000,000 samples and you have a pretty good idea of what the function is doing. But for a 1,000-dimensional function, you would need a lot more samples of the function. So that's kind of what I meant. But it's definitely a computational issue that you just cannot compute enough examples for it to be representative. Is the way I was thinking about it. All right, I guess we're and it's over. Oh, wait, there's one more comment. Yeah, Gurkin Glass is saying, thought more data is always better, but if you use enough data, it is more compute efficient. If there is enough data to use, then it's more compute efficient to use less data and more parameters. Yeah, so yeah, I think the scaling laws are kind of about finding a sweet spot between the amount of training data and the number of parameters used and the training time as well. I think it's like a kind of a nuanced art or science of figuring out the right training parameters.
Are there
Yeah,
any theorems where H was the set of deep learning neural networks?
Yeah, so I think that would be kind of one practical application to take H to be the class of functions represented by deep neural nets with a certain number of parameters, for example. I mean, there's, you can look at it in that setting where you just look at the functions. But I think like one sort of important discovery has been that part of the interesting thing in deep learning is just that the representation of the function is highly redundant by the neural network. So there's like it's a to map from the parameters to the function space, it's a singular mapping, because a lot of different parameterizations can often give the same functions. So yeah, a lot of the nuance in understanding neural networks specifically is about understanding like how singular that thing is, and I guess that's what singular learning theory is, the discipline that's focusing on it. But yeah, it's definitely a very kind of deep subject. It's been becoming very popular recently, I think.
Yeah, we used to feel like quite embarrassed to make our models too high dimensional in general, right? Because we thought, hey, you can't just
Overfitting.
keep adding parameters. You're going to explode the amount of data that you're going to need and the amount of compute that you're going to need to do. And then we had this idea, no, it should be possible. It should be possible with a good prior, right? There's always this idea, we could just do it Bayesian, then we can get over this problem. And it wasn't always true in practice. It was hard to really make that work. And then deep learning came along, which I don't know if people have decided whether it's in fact Bayesian or not. I don't know. I'm not really up to date with that, but it's not clearly based on a prior. Maybe it is in the architecture or something. I don't know. But it seemed clear that you can really keep adding dimensions to your hypothesis class, and something behaves very differently. There's some kind of different kind of dynamic happening.
I think it was,
yeah, go ahead.
I think it was a big confusion in statistics that really affected a lot of domains. That people had the feeling that if you have too many parameters, you have too many degrees of freedom, and so you cannot learn. And afterwards, people disappeared. That actually people, and now people, well, I say no, but maybe for 5-10 years, people have been understanding that there is a really bad situation where your amount of data is kind of proportional to your number of parameters counted in the right way. And there things go really badly. But when you add even more parameters, then actually it works again.
Very interesting, yeah.
Would that also work with just like a polynomial? So if you had a polynomial,
yes, it's a very general phenomenon. So it's even true for like linear regression.
No.
So for linear regression, maybe it's very clear that if you have noisy data and you have the same number of parameters as the number of data points in some sense, then you can just find an hypothesis that fits everything, but actually it fits the noise very much.
And then what kind of learning algorithm are you using in the regime where your number of parameters is much larger than the number of data points?
Well, you use some regularization or some prior, which is kind of similar.
Right. Interesting.
And
Yeah, so,
oh, sorry. I just have a
I was
question.
going to stop the recording.
Yeah, I can just keep asking questions. So I'm happy to stop.
Yeah, I stopped the recording now. We can, I guess, chat a little bit more.
Yeah, the level